Hi and welcome to my presentation on design and implementation decisions in type-driven development tools. Before we dive into the details of design and implementation decisions in type-driven development tools, let me first give you an overview of the topics that we will cover in this presentation. First is the abstract, followed by objectives of the study. Third, introduction, then methodology, followed by results and discussions, and then conclusion and recommendations, and lastly, references. Abstract. This paper explores the design and implementation decisions behind type-driven development tools, including the benefits and limitations of statically typed languages, the role of type inference, and how TDD tools can support incremental development, as well as the challenges involved in designing TDD tools that are both powerful and easy to use. The introduction, type-driven development is an approach to software development that uses types of or to guide the processes. And TDD tools assist developers by providing features such as type inference, type checking, and code completion. The use of statically typed languages in TDD tools can catch errors at compile time, but can also result in added complexity in writing type annotations and potentially restrictive type systems. Supporting incremental development is also critical in TDD tool design, and code completion features can, and in this process, overall designing TDD tools involves complex trade-offs between various approaches, making them easy to use for even a novice user. Objectives of the study. The main objective of this study is to explore the design and implementation decisions in type-driven development tools, focusing on the trade-offs involved in different approaches. Specifically, we aim to identify the benefits and limitations of using statically typed languages in TDD tool design. Evaluate the role of type inference in TDD tool design and implementation. Third, investigate how TDD tools can support incremental development. And lastly, highlight the challenges involved in creating TDD tools that are both powerful and easy to use. Methodology, a comprehensive literature review to investigate the design and implementation decisions in type-driven development tools, focused on research papers and industry publications that discuss TDD tool design and implementation, statically typed languages, and type inference in software development. Third, used a systematic approach and inclusion-exclusion criteria to identify relevant papers. Fourth, conducted a qualitative analysis of the findings to identify common themes and trends in TDD tool design and implementation. Identified key trade-offs and challenges in TDD tool design and best practices for creating powerful and easy-to-use TDD tools. And then for the results and discussion, okay. Okay, for the results and discussion, we have uh, on this table, we have five TDD tool design implementation decision and their corresponding example. The first one is type inference. The TypeScript language provides a type inference system that infers the type of variables and functions based on their usage. The next one is type checking. Example of the type checking, the Rust language provides a powerful type checking system that helps catch errors before the code is executed. Next, code completion, the IntelliJ IDEA or IDE provides code completion functionality that suggests code snippets and function signatures based on the types of variables and functions that are in scope. And then we have refactoring. The Visual Studio Code IDE provides refactoring functionality that allows developers to rename variables and functions safely. And lastly, error reporting. The ELM language provides clear and informative error messages that help developers identify and fix errors in their code. So let me give you an example on each of those TDD tools. So for the example of the type inference TDD tools, it involves automatically inferring the data types of variables inputs and outputs based on the context of the code. Here's an example. Suppose a developer is working on a function that sorts a list of integers. So the initial implementation of the function might look like this. So we have define, sort list, and then return sorted list. However, the developer might realize that the function does not handle cases where the input is not a list of integers. So to add type inference, the developer could modify the function to use type hints and add an assertion that checks the data type of the input. So here's the code. So with this modification, the function will raise an assertion error if the input to the function is not a list of integers. Next, the developer can write a test to ensure that the type inference works correctly. So this one. So this test will pass if the function correctly sorts a list of integers and raises an error if the input is not a list of integers. So overall, type inference in TDD can help ensure that the code is robust and can handle unexpected inputs, improving the overall quality and reliability of the code base. The next one is type checking. Type checking in test development or test-driven development involves checking that a function or method returns the expected data type or raises an error if the input data is not of the expected type. So here's an example. Suppose a developer is working on a function that calculates the factorial of a number. The input to the function is expected to be an integer. So the initial implementation of the function might look something like this one. So function factorial n, if n is equal to 0, it will return 1, else return n factorial n minus 1. However, the developer might realize that the function does not handle cases where the input is not an integer. So to add type checking, the developer could modify the function to include an assertion that checks the data type of the input. So here's the new function. So define factorial and assert as uh, is instance integer input must be an integer. So if n is equals to 0, return 1, else return factorial n minus 1. So with this modification, if the input up to the function is not an integer, the function will raise an assertion error with the message input must be an integer. So next, the developer can write a test to ensure that the type checking works correctly. So here's the code. So with this code, the test will pass if the function correctly returns the factorial of an integer input and raises an error if the input is not an integer. So overall, type checking in TDD can help ensure that the code is robust and can handle unexpected inputs, improving the overall quality and reliability of the code base. And then the next TDD code is the code completion. For the code completion involves using automated tools that suggest possible code snippets or completions as the developer is writing code. So here's an example. Suppose a developer is working on a function that calculates the sum of a list of numbers. The initial implementation of the function might look something like this. So we have sum, list, total equals to 0. For num in list, total equals plus equals sum, return total. As the developer is typing out the for loop, a code completion tool might suggest the use of the built-in function sum. Uh, So the new code, in this code, completion tool helps the developer write code more efficiently and effectively by suggesting built-in function that can achieve the same result with less code. Next, the developer can write a test to ensure that the function works correctly. So this and the bottom code. So this test will pass if the function correctly calculates the sum of a list of numbers. Overall, code completion in TDD can help improve the speed and accuracy of the development process, allowing developers to focus on writing high-quality code and tests. The next is the refactoring in test-driven development code. Involves modifying code base to improve its design, reliability, or maintainability without changing the external behavior. A typical example of refactoring in TDD is as follows. So suppose a developer has written a test for a function that calculates the area of a rectangle. So the initial implementation of the function might look something like this. We have defined calculate area, width, height, return width times height. However, the developer might realize that the function could be made more readable and reusable by creating a separate class for rectangle and moving the area calculation logic into that class. The refactored code might look something like this. So we have class rectangle and then define this one. So the test for the area calculation would still pass with the refactored code as an external behavior of the code has not changed. However, the refactored code is more modular and easier to understand, making it more maintainable and extensible in the long run. So overall, the refactoring in TDD is an iterative process that allows developers to continually improve the design and quality of their code base. while ensuring the code still meets the requirements of the test. And the next TDD code is the error reporting. For the error reporting involves creating clear and informative error messages that help developers quickly identify and fix issues in their code. Here's an example. Suppose a developer is working on a function that calculates average of a list of numbers. The initial implementation of the function might look something like this. So we have defined average list, return sum, and then length list. However, the developer might realize that the function does not handle cases where the input list is empty, which would result a division by zero error. So to add error reporting, the developer could modify the function to raise a custom exception. If the input list is empty, so here's the code that suggests. So with this modification, if the input list is empty, the function will raise a custom empty list error exception with message input list cannot be empty. So next, the developer can write tests to ensure that the error reporting works correctly. So this the new code to test will pass if the function correctly calculates the average of a list of numbers and raises a caution exception if the input list is empty. Overall error reporting in TDD can help developers quickly identify and fix issues in their code, improving the overall quality and reliability of the database or code base, sorry. So in this table, the levels of impact range from 1 to 3, and 1 being the lowest impact and 3 being the highest impact based on the 5 TDD codes that we've discussed. So in summary, the provided data is a list of TDD tool, design, implementation, decisions, and their corresponding levels of impact, with 1 being the lowest and 3 being the highest impact. Type checking and error reporting have the highest impact levels of 3, suggesting they are a high quality or high priority in TDD tool. Change implementation, type inference, and code completion have a moderate level of impact with a score of 2, while refactoring has the lowest level of impact with a score of 1. Type inference and code completion can potentially improve developer productivity, while refactoring is important to improving software quality over time. So overall, error reporting and type checking are uh, crucial aspects of TDD tool design and implementation. In conclusion and recommendations, type-driven development is an approach to software development that emphasizes strong typing systems to improve code quality and reduce errors. TDD tools support this approach with features like type inference, type checking, code completion, refactoring, and error reporting. This design and implementation decisions impact the development process in varying degrees and should be considered when choosing the best TDD tool for a project. Developers can benefit from using TDD tools to write better code more quickly and with fewer errors. It is recommended that the developers choose a TDD tool that best suits their project needs and skill level. And here are my references for my research. And that's end of my presentation, and thank you for watching.